Hello there. In this video, I want to go through this paper, Sample Size Determination Methodologies for Machine Learning in Medical Imaging Research, a systematic review. In this video, I will not go through any code, so this is just an overview of how we can estimate the sample size required for a training and what is the current method that people, especially medical imaging, are doing for estimating the training size. Also, it can be applied for other fields. So it mentioned the purpose of this study was to provide descriptive review of current sample size determination methodologies in ML applied to medical imaging and to propose recommendation for future work in the field. They reviewed many papers, and I just want to highlight the outcome of this. So they mentioned here the sample size determination methodologies identified were categorized as either pre-hoc or post-hoc approaches. So they said that there are two different methods for determining the sample size. First is pre-hoc, which is a model-based approach. I will explain that. And the second one is post-hoc, which is the curve fitting method. So in model-based, we should know the parameters of the model, and we have to calculate some mathematical formula in order to obtain what sample size we need based on number of parameters of the system. For example, it's mentioned a paper here that they said if we have a neural network with k units and d weights, this method predicts that for some classification error, a network trained on n images with fraction of 1 minus epsilon divided by 2 of the images correctly classified would approach a classification accuracy of 1 minus epsilon and unseen test dataset. So these kind of approach that we need some mathematical formula to do some pre-hoc, it's called model-based approach, that we need to estimate the size based on characteristics of the algorithm. So it said model-based approach provided sample size estimate based on characteristics of algorithm, allowed classification error, open generalization, and acceptable confidence in that error. These methods were based on the assumption that training and test were chosen from the same distribution. So this is another assumption that they mentioned. If we have like external validation, then maybe our expectation will not be met. So the next approach is the curve fitting that I want to highlight this one because in some complex models, especially in deep learning, if you want to estimate training size that we need, going to the pre-hoc method is difficult. That's why curve fitting relies on empirically evaluating model performance at selected sample size with a goal of extrapolating algorithm performance as a function of training set size. There are different approaches. First one is if we have a data and we split it to train and test, this is coming from the same distribution. We have a train set and we create n sample of size x derived from the training with replacement. So for example, we get n different sample set from the training set. And we train the model on them, and each of these S has X, exactly X number of samples. And after training and apply the result on the test set, so we can create these parts. So we have an average and a standard deviation of the result. Then we can repeat this, but this time we change the X. So we change the sample size for each S, and we repeat it, and we can create a graph. So based on that, we should see some sort of convergence that after Y sample size or a specific number of sample size, we are getting a consistent or at least very similar accuracy. This is one way. It's called an X subsampling. Another way is cross-validation. So if you want to do the cross-validation, we can split the data to X size again, but this time we want to do the cross-validation. So it's that the data is split into desired train size X and remaining test size Z minus X. In the previous method, we just separate the test set, but this time the test set can be different. I mean, the test set in the previous holdout method is consistent is the same data, but here we are applying the train on different tests. So each time we picked different subsample of the data for train and test, and we repeat that based on different value of x, the sample size, and we can create that curve. So there is another method called no repetition that is very similar to the holdout. We have a test set independent and consistent, but instead of creating different batches of data for training with same size, we can have different size like X, Y, and Z. And by replacement, we can repeat this experiment and create average and standard deviation, but also without any repetition, we can just have this one and create that plot. So there are some pros and cons for selecting different approach here. Let's back to the paper. It's mentioned here, model-based method may lack the ability to capture intricate of a specific machine learning task and must be tuned to bias variance trade-off and function generating mechanism of different algorithms. Curve fitting approach can be criticized for their need to perform empirical testing. Also, they mention here, validity of linear curve fitting approach is highly dependent on the algorithm, number of features, and their distribution. And finally, they give this suggestion that based on systematic review, researchers should attempt to estimate sample size requirement for their study using both pre-hoc and post-hoc, keeping in their mind their unique advantage and disadvantage. So I will go through that supplementary and will show you what is the advantage and disadvantage of picking each one of them. So let's go to the supplementary. In the supplementary, they are comparing the pre-hoc and post-hoc. Most of the thing here is covered during the presentation. So in terms of efficiency, the pre-hoc is fast, not computational demanding, because we need just some formulation to find out what is the best number of data sampling for training that model. But the post-hoc is computational demanding and require performance testing procedure. So for big models, especially in deep learning, maybe we cannot do that because just training a model may take a couple of days. The pre-hoc validated for simpler binary classification. So it's hard to create some formula for a model for multi-class classification or any other downstream task to find out what is the best number of samples that ensure the weights can be converged. But for post-hoc, we don't care about it because we are just doing some empirical approach. This can be validated for multi-class problem. And the pre-hoc, as I said, because it's hard to create such formula, it's good for low dimensional data, but the post-hoc can be applied for higher dimensional data. And as I said, post-hoc can be used for complex model. And finally, they said the pre-hoc can vary greatly based on method used and the machine learning task. Based on downstream task, maybe the sample size required is different. But for the post-hoc, it said error between estimated performance and actual performance can be less than 5%. So based on different methods, like as I said, the subsampling cross-validation may have higher variance of performance estimate at low subsampling size and low test size, respectively. We can get less than 5% accuracy for finding the appropriate sampling size, but depends on the number of samples that we have, the variance can vary. Yeah, so that's it. I think although this is for medical imaging, but it can be applied for any other approach, especially the curve fitting, which if you want to find out what sample size we need, and we have some limited sample size for now. So we can see and estimate how many samples we need for labeling. So I hope you enjoyed the video. Thank you. Have a good day.